We present the work on self-supervised category-level articulated object pose estimation, with part-level SE3 equivariance. Understanding articulated object poses is an important yet challenging step to help an intelligent agent to learn how to interact with the physical world. Prior works on articulated object pose estimation always rely on rich supervision to equip a neural network with pose estimation ability. However, considering the difficulty in acquiring such expensive annotations, they typically lose the opportunity to explore a wider application scenario. In this work, we take a step further and explore a pure self-supervised algorithm. In more detail, given a set of articulated objects from the same category with no additional annotations, we want to infer their articulated object poses, including part segmentations, articulated joints, and part articulation states. Designing algorithms to empower the machine with the ability to solve the problem is very challenging, considering the complex structure of articulated objects and the self-supervised setting without any annotation during training. To ease the above difficulties, we present our method, articulated object pose estimation with part-level SE3 equivariance. Given a set of articulated objects, we humans can easily parse them into a category-level canonical frame and articulated poses of each instance. Such two kinds of information correspond to part pose invariant features, which would not change as part poses vary, and part pose equivariant features, changing with part poses. Therefore, the self-supervised pose estimation problem is then converted to the self-supervised decomposition problem. Simply relying on common geometric features, with the above information deeply entangled for such decomposition, however, is a very ill-posed problem. Considering the part-level equivariance of part pose equivariant properties, we go further to pursue part-level SE3 equivariant networks to ease the difficulty of the self-supervised problem. By saying part-level SE3 equivariant features, we wish the feature of a specific part would change equivariantly to its own pose, while remaining invariant to other parts' rigid transformations. We then disentangle different kinds of information from such features. Then, together with a shape reconstruction-based self-supervised task, we can solve the problem in a fully self-supervised manner finally. Simply speaking, the convolution operation relies on estimated part poses, and the object canonical frame, to first define a canonical frame for each part. Then for each point, we communicate its neighboring point's features in its local frame, to acquire the part-level equivariance. Like shown here, when propagating the feature of point B to point A, instead of calculating at the original frame directly, we transform it to point A's local reference frame, saying point C, for communication. Based upon the point equivariant features, provided by the part-level equivariant network, we decompose part pose invariant and equivariant properties from them. For invariant properties, we predict part segments and a category-level reference frame. To further identify articulated object poses, instead of predicting the pose of each part individually, we decompose three trends of pose-related information. That is, a base part rigid transformation, joints information such as pivot points, and part articulation states. We then compose the predicted information to reconstruct input shapes. A simple shape reconstruction-based self-supervised task is added to train the network. Next, we present our experimental results. We conduct extensive experiments on 6 categories from 3 datasets to validate the effectiveness of our self-supervised pose estimation strategy. Our method can predict intra-category aligned canonical shapes for all tested categories with various kinds of articulated parts. They further make it possible for us to predict accurate poses. Our method can work well for partial shapes as well, validating its robustness to part occlusions. Based on estimated joint information, we can manipulate part articulation states and produce new shapes. As a visual evaluation, the part-level equivariant feature of the static part would not change when varying other parts' articulation states. Quantitatively, our method can outperform the unsupervised but in an oracle setting counterpart by a large margin on the articulated pose estimation task. For more information, please check our paper, project page, and code repository. Thanks for watching.